All right, hello everyone. I'm Rachit. I'm a professor at MIT, and I've been spending some time at Jane Street. And I have this weird artistically titled talk. I actually dropped the annual makers part because it was, anyways, you can ask me about it later. And y'all have seen truly a broad swath of PL research today, cutting through so many different domains. So it's pop quiz time, surprise. And I'll ask one really simple question, right? Like you've all been paying attention, you've been listening very carefully, so the answer should be easy, and I want to solicit answers, so you have to participate. Right? This is like a hostage situation, and you have to tell me. Okay, so here's a simple question. What is the fundamental goal of programming languages research? Just shout it out, and I'll reflect it back, so they don't need the mics. We have, say again? To improve the field, that's an answer. So what field? Programming languages research improves the programming languages field. Great tautological answer perhaps. Yes? Make humans use machines better. Great. I saw another one. Right. A nihilist answer. There is no fundamental goal. We do what we want. Yep.
I want to agree with that.
Okay, 2.
Make people happy when they're talking to computers.
Make people happy when they're talking to computers. All right. So there's some synthesis of ideas about being interfaces between computers and humans.
When it comes to verifications on kind of trusting the computer more.
Being able to trust the computer more, this machine that we created from scratch and should possibly know everything about, but we don't, so maybe we should trust computers better. Did I see another hand? Maybe 2 more, and then. Find the best abstraction to build a tool, so somehow convey our ideas better. Yes?
And radical, it's kind of what you mentioned, but just improve user experiences.
Improve user experiences, yes.
Make machines do what we actually want them to do.
Make machines do what we actually want them to do. So lots of themes about getting people and computers to interact and interface correctly, making them happier, making them express their ideas better. I'm actually going to hold off on my answer, and I want to go through a case study with you about some of the work I do and how this kind of a theme shows up and how I deal with the problems. So I want to tell you about this thing called an FPGA, a field programmable gate array. Maybe some of you have heard about. And it has an interesting history. So we were building more and more complicated processors, and these processors, their complexity can be reflected in the number of terms of the transistors they have inside them. So the Pentium 4 chip, for example, had 120 million transistors. The chips we have today are reaching tens of billions of transistors, but even at this point, one very important question sort of came up, which is we're building these chips. How do we know they're right? So there was one answer that was about making sure that the things we're building are correct somehow. And so this question of how do we test this thing that we're going to put into silicon before we put it into silicon, because it's really expensive and it's a lot of work to fix these things. Unlike software programs, we can't really patch them, so we have to get them right. And so before the existence of FPGAs, people would write computer programs to simulate the circuits that represented these chips, but those were not really scaling well. And so FPGAs are these black box. We'll see exactly what they are in a moment, but you can think of them abstractly as a black box that can simulate arbitrary circuits. And so you take your processor circuit and you map it onto the FPGA, and now you can simulate it much faster than you could have done by simulating it as a computer program. And then you can test that simulation and get some confidence that you've built the right thing. Right? So inside an FPGA, let's dive in, there's sort of this weird columnar architecture where you have these light blue things that are sort of logic. You can think of them as literally truth tables that you can program. And then state elements, which is something that can hold onto data, right? And turns out this is sufficient to simulate arbitrary circuits. You can take any sort of function you have and program the lookup tables, the truth tables in the blue part, and then if they need to store some information, you put them in the state. Right? But it's sufficient to simulate your circuits, but it's actually kind of quite slow because it's really hard, or it's really inefficient at simulating circuits that do a lot of arithmetic operations. And turns out if you look at a processor, most of the time what it's doing is some kind of math. It's adding numbers, it's multiplying them, not just in sort of the computational part, but also when it's deciding what next instruction to fetch or what kind of thing to decode or comparing two things. So there was this like gap where even though FPGAs are complete, they can express any circuit, they're really, really slow. And so the change people made was they added this thing called a digital signal processor. And again, in this weird columnar architecture. And digital signal processors are really just some circuit that can do adds and multiplies. And with all of this, we were able to build FPGAs that were able to efficiently simulate many of the circuits we care about. And so when you think about FPGAs, this is sort of a good enough abstract model of what's going on. But people are not, satisfied by using things for the reasons they were built. And so it turns out some very smart people realized that, well, this thing has the ability to store data. It can do some computation. And it can do this really, really effectively. It can do it in a really low latency way. So what we're going to do is we're going to build accelerators for our systems. We're going to take computations that used to run on a CPU, and we're going to turn them into circuits, and we're going to put them in the FPGA. So for example, if a packet comes in, normally the packet needs to be placed into the CPU's memory. The CPU has to wait, pull it, do something to it, put it back in the buffer, and the network sort of sends it back again for you. But with an FPGA on the line, sort of connected to the Ethernet, you can just take the packet off the wire, do the computation you want to it without going to the host, and send it back. And so people created a whole host of accelerators using these FPGAs. This is different from what they were originally designed to do, which was like taking arbitrary circuits and being able to simulate them. They were being used as accelerators. So I want to tell you about a very particular problem that shows up when you try to use FPGAs as accelerators, which is how do you program these things called DSPs, or digital signal processors, the green little things. So to do that, we'll understand what's inside a DSP. A DSP has this weird, complicating looking diagram, but you don't have to worry about it too much. It has a couple of adders, as I told you, and a multiplier. And so what you can do with this thing is you can perform computations that look something like this. You can perform a computation that multiplies two numbers and adds another number, and it's done, right? Except this is hardware we're talking about, and it's hardware, so it's going to be hard. And so one of the complexity in hardware is that you have to think about timing. You have to think about when signals are sent to your circuit. So for example, the real interface to a DSP like this is that the inputs A and B need to be sent on the first clock cycle. Input C needs to be sent on the second clock cycle. And then the output is produced on the third clock cycle, right? So this time, this notion of time is very fundamental to the way we program circuits. And so you look at this. As a PL person, I came into this, and I looked at this, and I was like, it's kind of really weird, right? Like this notion of time makes these interfaces so weird. It makes them so complicated. And so, like a good PL person, I was like, I'll fix it. I'll fix it. I know better than these hardware people, right? I'll fix them by removing all of the timing behavior. And so I want to pause here and sort of like reflect on this. I think a lot of the times when we do PL research, we do it because we have a really strong sense of aesthetics and what things should be elegant and nice and good. Not just they work, but they are actually fun and happy and make people happy in using them, as we heard, right? And I go back to this quote that a good friend of mine said to me in the first year of my PhD, which is this: as a community, we have a moral responsibility to step in and say, you are having fun, right? And it was a funny little quirk, but I think there is some truth to it. Again, we do work that is driven by aesthetics at some fundamental level, right? We have to sort of think about what is nice and elegant. But we also have this tension that we need to build tools that other people can use, right? A lot of the answers I got was, how do we build tools that make people happier when interacting with machines, right? And so you have two ways of dealing with the problem. You can either sort of watch communities, other people using systems of different kinds from the outside, and sort of analyze them from the outside, solve the problem for the outside, and sort of go away self-satisfied. Or you can take the approach, which I'll call the nomadic approach, which is you go to the community. I mean, this is not a profound revelation, but it's sort of like a thing that is, I think, useful to think about, which is what does it entail to going to the community, right? So for the specific problems of thinking about circuits, why do people care about timing so much? It comes down to efficiency of certain kinds. When we think of programs, there are sort of two ways you can think of hardware programs. They can be sequential in that they process one input fully before proceeding to the next one. Or they could be pipelined in that they process multiple inputs at the same time before the first one is done, right? And so if you go back to this DSP example, this thing that computes out equals to A times B plus C, and you connect the output back to the C, what will happen when I send in a stream of A's and B's? I'll pause here and wait for an answer, but feel free to ask me what the heck I just said. So I'm taking the output and putting a wire back to the C, and I'm sending in a sequence of A's and B's. Anyone? It's accumulating some of the products. Great. It's going to perform this computation, which we also know as a dot product implementation. But it's specifically a high throughput implementation of dot products because you can continuously feed it A's and B's, and even before the output is done, it can sort of keep accumulating the values, right? And this is enabled because you have this timing interface. And so it's not that timing is this weird thing that appears in these interfaces because the hardware people don't know what they're doing. It's actually timing is key to making efficient hardware interfaces. And sort of, if you look at the problem from this perspective, you come to a very different solution. You say, well, let's build a language that allows you to reason about time in some ways, right? And in doing so, you can use very classic PL tools. So that's what I did for my PhD. I built this language called Filament, reasons about timing. At a very high level, there's some notion of time embedded in this language. There are these events like that G. And once you have events tied to the clock, you can actually sort of specify when the inputs are required, when the outputs are produced. And this is sufficient to describe the timing behavior of circuits. And then I went around, and like a good PL person, I built some math around it. And I showed that if you use this type system that Filament provides, it's going to eliminate a certain category of bugs, right? That's what type systems do. They make sure that well-typed programs don't go wrong. But specifically, there's another thing I have to do, right? I have done this type systems work, and it's sort of fun and interesting. But again, I was doing it for the architecture community. And so I have some responsibility of explaining to the architects what this property I'm giving them is. Specifically, these structural hazards are a particularly nefarious kind of sets of bugs that occur when you build hardware where data corruption issues might happen. And so they're problematic because you don't get error messages when they happen. What happens is you'll just get silent data corruption or loss. And that's really problematic. And if I can go and sort of communicate to the architects in their language what property I'm giving them, that's a really nice outcome because now architects who might not have thought too much about type systems because, again, they're used to really powerful, complicated model checking tools that give them the ability to specify really powerful sets of properties, they can go and think, well, these type systems are actually quite useful for certain kinds of properties that I might care about. And so that's the second step, right? When you learn about a community's vocabulary and language, you can actually explain the problems that you have solved to them and sort of show that the work you were doing was useful to them, not just the PL folks that were listening. And so that's one part of what you should do if you're adhering to this nomadic way of doing programming languages research. I think the second one that I also think is really important is we go to these communities, we take our ideas, things like type systems, and we mold them to work for that community. Then we can bring back those changes to the community and show them how different folks use these ideas, right? I'm being too abstract, so going back to like this idea of the type system I built, it's built on this very sort of important idea in programming languages called a separation logic. And initially, separation logics were defined to sort of reason about properties of heap, like pointer manipulating programs, right? So if you have some program where x points to 10 and y points to 20, you want to be able to prove properties about x and y separately and then compose them. But if x points to 10 and y points to x, you want to be extra careful about the properties you're proving about y because changing x might change its value, right? And so separation logic often has this like very interesting concurrency rule, and fundamentally it's allowing you to reason about spatial resources, right? Things that exist on your heap or the stack or something. On the other hand, what we needed to do when we were doing this work on hardware circuits and something. We needed to reason about time as a resource, right? And so when you flip the script, go from sort of thinking about the separation of physical resources to the separation of time, that brings a new set of challenges that needed to be addressed with new formal foundations and new sort of interesting kinds of tools that connect the theory back to sort of more interesting work. And so in this, we take the complication of a field, distill it down to tools that the PL community understands, and bring them back as sort of interesting problems that we can solve together. And so that's sort of the high-level thesis of this talk, which is that if you do PL research that tries to sort of connect communities together, you should think about becoming experts in the other communities. It's really, really hard to observe people from the outside. As we just saw in the previous talk, it's sort of, you can't get the full source of truth. And one way to sort of account for it, it is a heavyweight way of accounting for it, is to become the expert and be able to speak their vocabulary. And you can sort of have impactful work, interesting work, and solve problems for real people. So I'll end with sort of my answer, which is very close to the answers I got, which is that like the fundamental goal of programming research is to sort of bridge the gap between humans and machines. But we have to take sort of a very broad view of what the word machine means, right? There's many, many interesting applications of PL tools and technologies. And we have to sort of connect with the human beings who are using these tools and really try to understand their problems. So that's my talk. I'm happy to take more questions. Thank you.
Okay, thank you, Rachit, for the great talk. Any questions from the audience?
So I have a question. When you go to these other communities, there's often this thing of we build some tool, we build some prototypes. Sometimes we call them like mini applications or something. And then sometimes the other community will say, oh, this isn't a real application, so I don't think this is actually useful to me because it can't handle the complexity of like my real software. Like, how do you balance this tension between proving to them that this is useful and the limited resource budget you have as a researcher to actually go implement these things?
Right, this is a great question, sort of getting to this tension of you want to do research and you want to build things that are demonstrably useful quickly and then do the next thing, and that's sort of important in being a productive researcher. But it also takes a lot of effort to convince someone from another community that what you have done is useful. I think the thing I have found successful, and that is perhaps just an existential proof, not a universally quantified proof, is you need people in that community to lend you moral authority in some ways, right? You have not, for example, I have not been an architect for 20 years. But if I can sort of connect with architects and really understand the problems they're working with and sort of understand the vocabulary, understand the depth of the problem, one of two things happens. Either they accept that some of it is incidental complexity and some of it is essential, and then you focus on the essential and trying to solve the essential, or you just convince them that this is a new way of looking at the problem that gets them the thing that they didn't even know they wanted, right? But there's sort of no easy way of doing that. I think it depends a lot on forming long-term connection with people and demonstrating to them that you actually hear and listen to the problems that they're working on. So it, again, sort of ends up being a problem about humans more than computer science. You have to forge those connections with people to convince them that what you are doing is useful.
Thank you. Thank you for the talk. Super cool case study. I'm curious, what was being a nomad like in your case? Who did you talk to figure out the timing thing? Was this like something you explored on your own? Or were you like trying to develop a PL and then you maybe did a user study with like some architects and they were like, you need time? How did that look for you?
It was, so the question is, how did I stumble upon this idea? What was the process? It was quite literally talking to an architect who was working on actually trying to use these DSPs effectively. And they were telling me, oh man, it's like, you're trying to do some of this stuff where you're abstracting time, but like actually, here's an example where it's kind of tricky. And I was like, I had the exact reaction that I sort of tried to role play here, which is, why is this weird temporal interface needed? And then they pointed out to me that you can do this like connection from the output to the input, and you get a high performance throughput. So that was the moment at which it struck that timing is not something you can just get rid of. It's sort of profoundly important in the way you think about hardware. So it was exactly the thing I demonstrated, I guess. But to understand how to sort of get to that point, I think during my PhD, there was a lot of just talking to architects and trying to understand what they're doing and why they're sort of designing programs in particular ways and so on. So it was sort of a long ramp up to getting to that point of finding that interesting conversation that incites an idea.
Rachit, I have another question. So I'm just wondering, like in the architecture community, what prevents the previous language designer from associating those kind of clock cycle temporal information with the wares? Like, because it's apparent that this kind of information is very useful for debugging, right? So just wondering, like, what prevents a previous designer from considering this factor?
Yeah, so the question is why is there this blind spot? And I think that's sort of maybe hard to understand. I think there's, in engineering circles, there's often sort of a feeling of like you have to go through the pain to build something really, really cool and important. So maybe they didn't do it for that reason. I think there's also just like, I don't know, I think timing is one of those things that you're taught to think about from very early on, and you don't want to change the language that you work with. Perhaps that's sort of the clearest answer I can give you, which is that when you do research in a field, you have to take things as invariants, things above you or below you. Like we don't, like if you are an architect and you have to build a new architecture, you're not going to worry about changing Verilog too much. You want to go build your cool architecture. So perhaps that's the reason, but I don't know if I can give sort of a fully confident answer of why they didn't do this already.
Yeah, that makes sense. I think we do have one more question there.
Thank you very much. Great talk. Something you kind of like hinted at is that the thing that you ended up with at the end, which is like this, you have these formal semantics and like this like language with this typing system, and then there's sort of this implication that there's also an implemented version that you could like actually really program in it, would really like generate circuits. How did you balance in the development process of like coming up with the theory and like implementing the theory and like iterating on things? What did that development process look like? Because often things, you just kind of get what the end result is.
Right, so the question is about sort of what is the path from conceiving the idea to implementing it and sort of making it useful in a way so that architects think about that being useful. I think that's a really interesting question, and I think the development process was tailored very much to build something that is very recognizable to the eyes of an architect. And what that means is building something as close as possible to Verilog. So that language I showed you truly only has one novel construct, and everything else is just like equalities that you get to write. And the way it proceeded is actually we knew that once we knew about this problem, we wanted to sort of capture timing behaviors. So we built sort of these interfaces and then tried to write down the term language and refine it so that it's the simplest thing possible, right? And so once that was done, once we were able to have the implementation working and have sort of a back of the paper able to convince ourselves that it gives us this property, then we went and wrote down the formalism. But that's just like the way I end up working with formalisms. I like to build things first and then formalize them.
We know that there are some hardware description languages such as Verilog, Gcell, and I mean, is your work built on these languages, or you are writing your own DSLs?
Yeah, so the question is, are you building on existing work, or is there a new language? I think there's always an interesting tension in programming languages research of like, yes, do you want to take the complicated system and immediately build on top of it, or do you want to build a small core language? This project took the small core language because, again, I wanted to sort of show that it is possible even in the sort of very unstructured case of arbitrary hardware designs. But the ideas since then have been, you know, in the process of being applied into various contexts. So I mentioned I'm working at Jane Street. One of the things I'm doing is actually taking this idea and trying to port it into their internal hardware description language, which is like Chisel.
Oh, thanks.
Yeah.
So before you realized that you want to solve this problem in this specific domain space, like what was your process of exploring different areas and then settling for this and like a particular place to ask questions to people and then see what kind of problems they're facing to maybe come up with a solid concrete idea? But what was the process before that?
Right, so this is a question of like what happens before you even reach to the domain that you care about. In my case, I just thought architecture was kind of cool, and I wanted to do it. And my advisor was someone who was an architect also. So for me, it was really, I was just curious about how these people work and what kinds of systems they're building. There's also sort of an emerging need to build more and more hardware with the end of Dennard scaling and Moore's law and those kinds of things. So I was interested in that kind of stuff, and then the collaboration started because I was working with my advisor. And that can often be a pretty good impetus, which is like, you have some friend you really like in your PhD program, and they're working on something interesting. Why not try to learn about what they're doing, and that might spark sort of the collaboration. For me, it came from my advisor and sort of just generally being interested and curious about architecture research. Yeah. Cool.
Hey, any other question? Okay, please.
You said you changed the name of your talk from like a longer name to this. Can you elaborate on that more?
Yes, so there was this anvil makers thing because I had this whole convoluted thing about how we don't actually make hammers, we make the things that are used to make hammers. And I just thought it would be too complicated to explain in a talk, so I decided to not do it. Right, great question. All right, thank you everyone. I hope you had a lot of fun.